Hi everyone, I'm Sudarshan from Aarhus University, and today I'll be talking about fair division under generalized assignment constraints. This talk is based on joint work with Siddharth Barman, Arindam Khan, and KV and Sreenivas. This work addresses problems in the fair division space where we have some agents, some goods, and the goal is to allocate the goods among the agents fairly. And here's the key takeaway from the talk. We show a bunch of positive results showing that strong fairness guarantees can be achieved under constraints with charity. Now I'll talk a bit about the setup. We have some agents, and each of the agents has a budget. The budget is meant to limit the amount of goods that each agent can have. This is in contrast with the unconstrained fair division case where, in principle, we can assign any subset of goods to any of the agents. Secondly, we have some goods. The goods can be of two types. They can be indivisible goods, and of which some examples are cars or some artifacts like paintings, etc. And there can be divisible goods. And some examples of divisible goods are cake or pizza, which can be cut into arbitrarily small pieces and distributed among the agents. Lastly, we have valuation and size functions. These functions tell us for each good how much an agent values it and how much and what size the agent perceives the good to be. These functions are assumed to be agent specific and additive throughout the talk. As mentioned earlier, for a problem in the fair division space, the goal is to allocate the goods among the agents fairly. In this slide, I will talk about the fairness criteria we will be using throughout this talk. The first important thing to note is that the standard idea of and definitions of Envy-Freeness do not make much sense in the case with constraints. This is because in most cases, Envy-Freeness cannot be guaranteed and is unreasonable. This is one of the reasons for this is because of the asymmetry among the budgets of the agents. To give you an example, let's consider the case as in the figure with two agents. As we can see in the figure, the budget of the green agent is much smaller than the budget of the red agent. And it is unfair to expect that the bundles assigned to each of these agents will have comparable values. So to get around this, we come up with a new notion of feasible envy-freeness, where we only compare feasible subsets of goods. That is, in the figure, the green agent looks at red agent's bundle and compares the value of her bundle with all feasible subsets of the red agent's bundle. Another important thing to be mentioned in this case is that because of the budget constraints, sometimes it might not be feasible for us to be able to allocate all the goods among the agents. This can happen if there are many goods and agents have very small budgets. This means that not all of the goods can be assigned to the agents and such that the budget constraints are satisfied. In this case, we define the construct of charity who gets all the unallocated goods. Coming to the main results of the work, for the divisible goods case, we show that there always exists a feasibly envy-free division. Moreover, we show that we can always compute such a division efficiently. For the case of indivisible goods, we define a slight relaxation of the notion of feasible envy-freeness called feasibly envy-free up to any good. For this fairness notion, we show that there always exists an allocation satisfying this fairness criteria. I'll talk a bit more about this in detail when I get to this case. For now, I'll start by describing the divisible goods case in detail. This is the framework of the divisible goods case. As mentioned earlier, we have agent-specific value and size functions for each good. Vi of g and Si of g gives us the value and the size of good G as perceived by agent I. Throughout this section, I'll assume that the value and size functions are additive in nature. Further, for each agent, we have an individual budget constraint which limits the amount of goods that can be assigned to that particular agent. Specifically, the budget constraint limits the size of all the goods that can be allocated to that particular agent. As mentioned earlier, it might not be possible for us to be able to allocate all the goods to the agents. For that reason, we define the construct of charity who gets all the unallocated goods. Coming to the formal definition of feasible envy-freeness, we say that agent I does not envy agent J if agent I prefers her bundle over every feasible subset of agent J's bundle. Further, we say that an allocation is feasibly envy-free if the following two conditions hold. First, we require that no agent envies any other agent. And second, we require that no agent should envy the charity. The last condition is especially important to avoid the case in which we assign all goods to the charity. In this case, all the agents will have empty bundles. Although no agent will envy any other agent, this is obviously not a desirable scenario. Now I'll talk about the algorithm which computes a feasibly envy-free division for the divisible goods case. For that, we define a quantity called the density of a good. This is again an agent-specific function which is defined to be the value of the good over the size of the good as perceived by agent I. A key technical contribution of our work is to come up with a condition called density domination. I'll describe this condition on a very high level. For a threshold vector tau, which is an n-dimensional integer valued threshold vector, we define the condition of density domination as the following. First, we restrict the goods allocated to agent I to be only from among the top tau I densest goods according to her. In addition, there is a domination requirement which says that each good is distributed equally among the agents to which the good is assigned. This is a very high level idea, and I would recommend you all to check out the paper to read about this in detail. But why is this construct important? Firstly, we show that the condition of density domination implies feasible envy-freeness. And secondly, given a vector tau, which is a threshold vector, the condition of density domination can be written as a set of linear constraints, which in turn is crucial for us coming up with the polynomial time algorithm. Here is the actual description of the algorithm. First, we initialize the threshold vector tau to be the all ones vector. Intuitively, it means that at the very beginning, to each agent we only assign the densest good according to them. Then we check for density domination for this particular tau. We do this using a linear program. Recall that the density domination condition can be modeled as a set of linear constraints. If this following linear program is feasible, then we compute the allocation and terminate. In case the linear program is infeasible, we update the threshold vector tau as follows. We choose a specific agent I, depending on some criteria. We update the value of tau I by incrementing it by 1, and we repeat the whole thing again. We show via a slightly intricate argument that this thing always terminates and we always end up with a feasible linear program. Here are a few salient features of the algorithm. First is that we use linear programs to model the condition of density domination, which in turn we use to find a feasibly envy-free division. This in turn gives us a polynomial time algorithm. The algorithm is polynomial time because in each step we run a linear program which is run in polynomial time, and we show that the updates can only occur a polynomial number of times. A slightly interesting and technical point is that we show the existence of feasibly envy-free divisions using this algorithm. And this algorithm does not rely on fixed point arguments, which has been used to prove the existence of fair divisions throughout the history of fair division. To sum up the divisible case, we show that if we have divisible goods, there always exists a feasibly envy-free division, and moreover, we can find such a division efficiently. Coming to the case of indivisible goods, I'll first talk a bit about the framework for indivisible goods again. Firstly, it is important to note that feasibly envy-free allocations do not always exist. The standard counterexample is where we have two agents and a good which fits in both of their budgets. If we'll have to assign that good to one of the agents, and the other agent will inevitably end up envying the other agent. So in turn, we define a relaxation called FEFX, or feasibly envy-free up to any good allocation. This is analogous to the relaxations that have already been done in the unconstrained indivisible goods case by Karagiannis et al., who defined the EFX notions. And here's the formal definition of the FEFX fairness criteria. Under FEFX, we say that agent I does not envy agent J if she prefers her bundle over any strict feasible subset of agent J's bundle. So, to give a bit of intuition about why this condition is called FEFX, we use the following example again. Let's consider the case with two agents, the green agent and the red agent, with their respective bundles. Let us say we have to check if the green agent envies the red agent or not. Another way to check this under the FEFX criterion is the following. We choose an arbitrary good, that is, we choose any good from the red agent's bundle. Let's say the red good here. We remove it for the purposes of checking envy. We remove the red good from the red agent's bundle, and now the FEFX criteria is equivalent to checking the standard feasible envy-freeness. That is, we say that the FEFX criteria holds if the green agent prefers her bundle over any feasible subset of goods in the red agent's bundle. Hopefully this gives some intuition about why this is similar to the EFX notion defined for the unconstrained case. Here is the algorithm we use to prove the existence of feasibly envy-free up to any good allocation. Before going to the algorithm directly, I'll talk a bit about the problem of finding such an allocation. Firstly, we show that the problem of computing an FEFX allocation is NP hard. So unless P is equal to NP, we don't have any hope for a polynomial time algorithm. Next, we do the next best things possible, which is we give a pseudo polynomial time algorithm and an FP for the same problem. And the key idea behind the algorithm is to swap minimally envied subsets. And this in turn is inspired by previous work by Chaudhary et al., who kind of do the same thing, but in the unconstrained case. And here's how the algorithm actually works. Before the algorithm, however, I'll define the concept of minimally envied subsets. A set of goods is called a minimally envied subset if the following two conditions hold. First, if there's some agent who envies that subset of goods. And secondly, we say that no agent envies any strict subset of that goods. And we use the construct of minimally envied subsets as follows. And here's the algorithm. First, we start with all the goods assigned to charity. So initially, all the agents have no goods and they have empty bundles. In each step, we choose a minimally envied subset of goods from the charity. As you can see in the figure, we choose a minimally envied subset of goods, and let's suppose that the red agent envies that minimally envied subset. In the next step, we swap those two bundles of goods. That is, we assign to the red agent the minimally envied subset from the charity, and we add the goods originally in the red agent's bundle back to the charity. And next, we repeat this process until no agent envies the charity. And that's the whole algorithm. And here are a few key insights because of which the algorithm works. First is that swapping minimally envied subsets ensures that the FEFX invariant holds among the agents all the time. And secondly, the stopping condition ensures that no agent envies the charity. This is true by definition because we keep on swapping the minimally envied subset until no agent envies the charity. And the proof that the whole thing converges relies on the fact that the value of exactly one agent increases strictly in each step, and the number of times this can happen is bounded. This gives us the main result in the indivisible goods case. That is, there always exists a feasibly envy-free up to any good allocation. So those are all the new results I wanted to talk about in this talk, and I'll conclude with the summary of the results we discussed. First, for the divisible goods case, we showed that there always exists an allocation which satisfies the fairness criteria called feasibly envy-freeness. And moreover, we gave a polynomial time algorithm which computes such an allocation. In the case of indivisible goods, we gave a constructive proof that an allocation always exists that satisfies the fairness criteria of FEFX. Next, we showed that computing such an allocation is an NP-hard problem. So there's no hope for a polynomial time algorithm unless P is equal to NP. And then we do the next best things, assuming because of the NP hardness. That is, we give a pseudo polynomial time algorithm and an FP test for computing an FEFX allocation. So that will be the talk. Thank you for the time.